Let's take a look at two elementary reactions that combine to form an overall mechanism for a chemical process. The first step is slow, and the second step is fast. We have H2O2 combining with I minus to form H2O and IO minus. And then IO minus reacts with H2O2 to form H2O, O2, and I minus. The first thing we want to do is write the chemical equation for the overall process. So we're going to cancel out any species that show up on the product side of one reaction and the reactant side of another. In this case, we can cancel out IO minus. You'll also notice that we can cancel out I minus. We're going to talk about that one because this is special. I minus shows up first as a reactant in the first step and then shows up as a product in the second step. So let's write the overall process and then we'll talk about I minus. So we have H2O2 plus H2O2, so that's 2H2O2, and that's aqueous. That goes on to form 2H2O plus O2 gas. So IO minus is an intermediate. It shows up on the product side of this reaction and then is used up as a reactant in the second reaction. So IO minus is an intermediate. What about I minus? It shows up as a reactant, and it reacts, and then it shows up in a product in the second reaction. Basically what that's saying is that it isn't consumed during the reaction. And so that means it's a catalyst. So catalysts are not consumed during a reaction. They also make the reaction occur more quickly. Still, it does not show up in the equation for the overall process. There are ways to indicate that this reaction requires a catalyst, but at this point we don't need to worry about that. So because we have two elementary steps combining to form our overall process, we need to determine what the rate law is for this overall process. So it's not directly, can't just look at our reaction and know what our overall reaction and know what the rate law is going to be. However, we are given two pieces of information. We know that this first reaction is slow and the second one is fast. For mechanisms where the first step is the slow step, we can determine the rate law from that slow step. So in this case, we're going to look at this first slow step, which is an elementary reaction, and from that, write the rate law. And I'm just going to write it, and then we'll see which one of these corresponds. Rate equals K, our rate constant, times H2O2 times I minus. And so that corresponds with the first option here. Now, please note that the catalyst does appear in the rate law, and that is allowed. Catalysts can appear in a rate law. However, an intermediate cannot appear in the rate law. Okay, so we said that the rate is equal to K times H2O2 times I minus. So that's from our previous slide. Now, if we take a look at the mechanism, we have a slow first step and a fast second step. Is this energy profile potential energy diagram consistent with the proposed mechanism. So we have our reactants, and we can write these on the diagram. We have H2O2, and we have I minus for our reactant. For our products, we have H2O2, H2O, O2, and I minus. We stated previously that we have an intermediate, and that was the IO minus. So we can put that in a valley. We have two different hills with signifying transition states, and each reaction is going to have a hill, so each step is going to have a hill. So we've got hill 1 here, hill 2 here. So that's consistent with our two-step mechanism. You'll also notice that the activation energy for the first step is quite large. For the second step, it's quite small, which is consistent with having a slow first step and a fast second step. So this suggests that our energy profile is consistent with the reaction mechanism. Let's look at a couple other examples. We have a reaction of 2A plus B forming C plus D, and it was determined that the rate law is equal to the rate constant K times the concentration of B. Which of these two options is consistent with the rate law? In both options, we have a slow first step and then fast steps after that. We can write for mechanisms with the slow first step, we can write a rate law based on that slow step. So in option A, our rate law would be equal to K times the concentration of A times the concentration of B. For option B, again, that slow first step, we would have rate equals rate constant K times the concentration of B. And given that, we would say that option B is consistent with the rate law. In this example, we have an overall reaction of 2NO2 plus F2 forming 2NO2F. And there's a proposed mechanism for this reaction. In step 1, which is our slow step, we have NO2 plus F2 forming NO2F plus F. And then step 2, we have NO2 plus F forming NO2F. We have some experimental data. This is an initial rate type reaction. So we have initial concentrations of NO2 and F2, and then the rates they're given associated with the concentrations of the reactants that are combined. And so can we do which of these things? The experimental data prove that the mechanism is correct, prove that the mechanism is incorrect, or are consistent with the proposed mechanism. So given that we have a proposed mechanism with the slow first step, we can write a rate law for that. And it would be rate equals K times the concentration of NO2 times the concentration of F2. With this experimental data, we can also predict a rate law. And if we look at how the concentration of F2 is changing, we hold NO2 constant, and how the rate is changing. For F2, we can see that we have a concentration of F2 for trial 2 over the concentration of F2 at trial 1 raised to some power is is equal to the rate for trial 2 over the rate of trial 1. And so we have 0.03 over 0.01 raised to some power equals 75 over 25. We will find that we'll have 3 raised to some power equals 3, and that power must be 1. So the order with respect to F2 must be 1. So we're going to have rate equals F2 raised to the power of 1. If we're looking at determining the order with respect to NO2, we can look at trials 1 and 3. We see that the concentration is doubling going from trial 1 to trial 2, and the rate is doubling going from trial 1 to trial 2. And that is consistent with an order of 1. I've got my rate constant here. And so if we look at the experimental data and the rate law from that, as well as the rate law predicted from the proposed mechanism, they are the same. And so we know that B is not correct. Okay, we have not proven that the proposed mechanism is incorrect. Have we proven that the mechanism is correct? Not exactly. It is not possible to prove that mechanisms are correct, but we can say that experimental data are consistent with the proposed mechanism.